In this lesson we're going to look at solving this particular equation here. Solve z to the 4 equals 16. Now this initially might look like a really simple equation because you think, alright, what number to the power of 4 gives you 16? And straight away you could probably say that just by inspection you know that z would equal 2 because 2 times 2 or 2 to the power of 4 does give you 16. You might also see that z equals negative 2 would also work. But there should be 4 solutions. Using conventional math methods, we've only got 2 solutions. So what we're going to do, in the previous example we looked at, this was actually a complex number. In this case it's a real number, but we can treat it as a complex number and solve our problem. So what we're going to do is we'll say we're going to convert 16. We're going to convert 16 to complex polar form. Now 16, if we were to draw our diagram, 16 is somewhere out here. And so it's really easy to see that the modulus of that complex number is actually 16 because that's its distance from the origin, and its argument, the argument of z to the 4, is actually 0 because it's right on the axis. So we know that this is actually 16 cis 0. Okay, in the previous example we had to do quite a bit of calculation to turn 16 into polar form, but when it's just a real number like this, it will always be 16, it'll be whatever the number is there, cis 0, because that's where it is on the axis. Okay, but we know now that we will get the same position if our angle is not only 0 but any multiple of 2 pi, because we're going to keep coming back to the same point. Now the reason we put that in is so that we actually get our 4 solutions. So now we can say therefore z equals, using de Moivre's theorem, we've got to get z, we need to raise z to the 4 to the power of a quarter. So we're going to get 16 to the power of a quarter, cis a quarter of this. Now who cares about the 0 plus, because it makes no difference, but we've got 2k pi times by a quarter, where k equals 0, 1, 2, and so on. Alright, so now we've got z equals, we can set about finding our 4 solutions. So we say if k equals 0, our first solution will be 16 to the quarter, which is the fourth root of 16, which is actually 2. Cis, if k equals 0, we'll get 0. 2 times nothing is nothing. If k equals 1, our second solution will be 16 to the quarter, still 2. Cis, k equals 1, we'll get 2 pi on 4. Or 2 cis pi on 2. If k equals 2, our third solution will be 16 to the quarter, which is 2, cis, k equals 2, 2 2's are 4, pi on 4, which is 2 cis pi. Our fourth solution, k equals 3, z4 will equal 16 to the quarter, which will be 2, cis, k equals 3 will be 2 3's are 6, pi on 4, which is 2 cis 3 pi on 2. Now in a moment we're going to convert these to Cartesian form. We'll revise how to do that, but just let's have a look and see where these solutions are on our Argand plane. So our first solution was at 2 cis 0. So remember, 2 is the distance from the origin, 0 is the angle to the positive real axis. So 2 cis 0 is going to be there. That distance out is 2. 2 cis pi on 2. So pi on 2 is 90 degrees, so it's going to be 2 units out this way. 90 degrees around. There's another solution. A third solution is at 2 cis pi. So pi is the angle, so we're coming all the way around to here. 2 units out there. And our fourth solution is at 2 cis 3 pi on 2. This is 2 pi on 2, or pi. This is 3 pi on 2 down here. So 2 cis 3 pi on 2 is down here. So here we've got Z1, Z2, Z3, Z4. Now this one is obvious. These two are obviously on the real axis. So this is 2, this is minus 2. So those are the two solutions that we originally looked at. The 2 and the minus 2 on the real axis. But here we've got the other two solutions on the imaginary axis. Notice also that there needed to be 4 solutions, which we've got. Needed to be 4 solutions, and the 4 solutions are equally spaced around the circle. Okay, in this case it divides the circle up into 4, so it's 90 degrees between the circle. Something interesting to note is that because this is a real number, then the solutions are symmetrical about, or the real solutions are on the real axis. You might remember in the previous example we looked at, the solutions were equally spaced, but they weren't. They were slightly twisted. That's because the original question we had a complex number here rather than a real number. Okay, so just a reminder, I said I'd show you how to convert these back to standard form or Cartesian form. 2 cis 0 is 2 cos 0 plus 2I sine 0. Okay, and cos of 0 is 1, so 2 times cos 0 is 2, plus sine of 0 is nothing, so it's just 2. In this case, here we've got 2 cos, let's put brackets this time, cos of pi on 2 plus I sine of pi on 2 equals, now cos of 90 is 0, so that's 2 times 0 plus sine of 90, sine of pi on 2 is 1, so it's 1i, so we get 2i. This one here, we've got 2 times the cos of pi plus I times the sine of pi equals 2. The cos of pi is negative 1 plus the sine of pi is 0, so we've just got negative 2. So here you've got your 2 and your negative 2. Here you've got your 2i, and then no guess as to what this one will be. This will be your minus 2i, so you've got 2 cos of 3 pi on 2 plus I sine of 3 pi on 2. The cos of 3 pi on 2, if you put in your calculator, you'll get 0. And the sine of 3 pi on 2, you'll get negative 1i. The I is there, so you get negative 2i. So there you've got your 4 solutions: 2, 2i, negative 2 and negative 2i. Notice here this is really a complex polynomial, very simple one. Z to the 4 minus 16 equals 0. It's a polynomial. It has real coefficients, so the complex roots, the 2i and the minus 2i, notice they're conjugates. The imaginary part swaps signs, so this is 2i, this is negative 2i, so they're conjugates.